I'm going to run you through the lesson 7.1 study guide. We're learning exponential functions this chapter. So an exponential function has the form y equals a times b to the x. They call that b the base because that's the thing that's taken to the x power. So x is our exponent now. Today it's all about exponential growth, which means things are getting bigger, and that just means our base is bigger than 1. And we'll talk more about what an asymptote is. It's kind of an imaginary line that helps you graph. So this first example is a good one just to take to heart. They start by just making a table of values for y equals 4 to the x. So they went -2, 4 to the -2, flip it and square. 4 to the -1, flip it. 4 to the 0, anything to the 0 is 1. 4 to the 1. 4 to the 2. Hopefully you see how they got those points, and when they go on the graph, you probably see why it's called exponential growth. It starts so low, and then look how fast it skyrockets to the sky, because those exponents are really powerful. One thing I want you to know is just that general shape of the curve. They're all going to look like that today, exponential growth. And then right here, in this case, it's the x-axis. I made that a little bit high, but the x-axis is what we call the asymptote this time, or the line y equals 0 is the asymptote, because do you see these numbers? They're going to continue as we do more and more negative exponents. They're going to continue to be smaller and smaller fractions, but they'll never go down to 0. So this curve, likewise, will get closer and closer to that line, but never quite touch it. That's the idea of an asymptote. And one big thing I just want you to notice is this point right here, the point 0, 1. You'll see that a lot because anything to the 0 power is 1. Let's practice a couple more. Here we have a 4/3 to the x. It's bigger than 1, so it should be a growth, 4/3. And what I want you to do is just do a few exponents. How about a -1, a 0, and a 1? 4/3 to the -1, that's just going to flip it over. 4/3 to the 0 is 1. 4/3 to the 1 is 4/3. And if we just plop those 3 points on the graph, we're going to see that general shape. Now it looks like it could be a straight line right now, but you need to know that exponential growth has that shape every time. Yeah, we'd still have that asymptote on the x-axis. That's not going to change very often at all, unless we start shifting up and down, right? Here's one. I'm going to do this one a little differently. It's got some complications. It's got a vertical reflection and a vertical shrink, but I'm going to focus on that 3 to the x. We're going to use that as our parent function. So -1, 0, 1. So that'll be 3 to the -1, 3 to the 0, 3 to the 1. And if we can plop those points on there, and then we'll deal with reflecting and shrinking. So we could do this kind of two ways. We could actually just take each of those points, their y values, times the -1/3. Or if you wanted to, you could flip and then shrink. I think -1/3 will work fine. So this point's already at 1/3. So if I take that multiplied by -1/3, it'll be -1/9. So it flips it and squishes it closer to the axis. This number that was up at 1, 1 times -1/3 is -1/3. So again, it flipped it and then squished it towards the axis. This one will be easier to see. So if we take this one, 3 times -1/3 will be -1. Again, because if you flipped it and then squished it 1/3 of the way back to the axis. So that doesn't really look like growth to me because of that reflection, but the asymptote is still happening. It's just kind of on the other side of the asymptote because of the flip. Here's a sweet one. Do you see the little 3 to the x in there? So again, I'm going to start with my 3 to the x graph. That should be okay, right? Just getting those points on there. You can see how that's going to grow. And then we just have to think about the transformations that happen here. So I like to start with the number multiplied in front is our vertical stretch. So I'm going to do that first. I'm just doing it in a light color because it won't be my final answer. That just means I'm going to take each of those points and double them. So this one was at 1/3, now it's at 2/3. This one was at 1, now it's at 2. This one was at 3. Times 2 is 6. All right, so that's my intermediate stage. Now let's do the final answer where we're going to do some shifting. You see that x plus 2 in the exponent? You could almost think of that as being in parentheses. So that's a left-right sort of thing. And in this case, a left 2, since it's opposite of how it looks. Then the -1, that's our vertical. And that would be a true down 1. So each of those light blue points is going to go left 2, down 1, left 2, down 1, and left 2, down 1. Can you see that my asymptote must have moved too? And it was the down 1 that messed everything up. So now our new asymptote is down at y equals -1. Just sort of a grid line that exponential curve follows. So here's a few more. 5 to the x. Can you picture it? And maybe you can even do these in your head, right? To the -1, to the 0, and to the 1. So 1/5, 0, 2, 3, 4, 5. Did I get that right spot? And again, as long as you know that general shape, you're going to be fine. Alright, this one, I'm going to go for that parent function first. I'm going to do a 4 to the x. So a 1/4, 4 to the 0, and 4 to the 1. And now I'm going to squish it down, right? That 1/3 is going to be a vertical shrink, so I'm going to take 1/3 of each point. This one was up at 1, so now it's at 1/3. What's 1/3 of 4? 4/3. What's 1/3 of 1/4? 1/12. I can't even draw that, but it just gets really squashed down. How does that look? So it doesn't grow quite as fast because of that 1/3, but it'll still get there. The next one, a 2 to the x. 2 to the x, so 2 to the -1. 2 to the 1, or sorry, 2 to the 0 is 1, and 2 to the 1 is 2. And then what are we going to do with those points? We're going to move them left 1 and down 1, left 1, down 1, left 1, down 1, left 1, down 1, left 1, down 1. Draw that nice smooth exponential growth, and there it is again, that down 1 causing our asymptote to be down at y equals -1. A little application. This is good for if you're trying to grow your money in a bank account. The compound interest formula is a special case of a times b to the x, only it has some fancy letters in there. I'll just do an example so you can see what all of that is about. So you have $3,000 to put in the bank. It pays 3.12% interest, compounded monthly. P.S. that 3.12 is an annual interest rate. Compounding monthly means that they're going to add a little interest every month, and then you can actually make interest on top of your interest. Like, you earn interest on that extra interest money that was put in there. We're going to find the balance after 2 years. So A is the balance after 2 years. We're starting with our initial deposit was $3,000. This 1 plus just ensures that we can get to keep 100% of our $3,000 plus a little more. When you enter the interest rate, just be careful that you put that into a decimal. So 3.12 as a decimal would look like that. Compounded monthly. That means every month we get that interest. So the number of times per year the interest is added is 12 times per year, monthly. And then the power is going to be that 12 times how many years? So after 2 years, we'll have interest added 24 times, yeah? Now maybe the only part that's going to mess you up is trying to type that in, so I'm just going to quick show you how that would work. You can mostly just type all of this in at the same time. I have one word of caution, and that's the exponent. Depending on your calculator, you have to be careful. So what I usually do is I usually multiply that in my head. 12 times 2 is 24. So I just put the exponent as a 24. And since it's exponential growth, it shows that we grew our money. And so our answer is about $3,192.90. It rounds to 91 cents. Do you think the bank would give you that, or would they short you and call it 90 cents? I'm not sure. Just one more example. Make sure you got this. This time we only have $2,000 to put in the account. We're going to keep 100% of that money, and don't forget to change that into a decimal. We have to divide that because that's a yearly interest rate, but we're only getting it compounded quarterly. How many times a year is that? 4 times a year. So 4 times a year, they're not going to give us the full 2.75. They're going to give us a fourth of that, but give it to us 4 times a year. It's a good deal. And then to the 4 times 3, right? Because 4 times a year for 3 years would be 12 times a year. Should we try typing it in? All right. Oh, I forgot. Divided by 4. To the, and I'm going to do it to the 12th power. So still exponential growth, still making some money. $171 worth. And this one rounds to 38 cents, and I'm sure they would round it down and we would miss out on those fractions of a cent. All right, that is exponential growth. Best wishes.